My name is Nadia, and I'm a senior machine learning engineer at NILAS. Today, I'm here to introduce you our next speaker at this TMLS in Finance conference. Before starting, I would like to remind you that if you have a question, please post it in the chat. I will collect all the questions and ask them directly to our speaker after the presentation. Our speaker of today is Igor Halperin. Igor Halperin is an AI research associate at Fidelity Investments. His research focuses on using methods of reinforcement learning, information theory, and physics for finance problems, such as portfolio optimization, dynamic risk management, and inference of sequential decision-making process of final agents. Igor has an extensive industrial and academic experience in statistical and financial modeling, in particular in the areas of option pricing, credit portfolio risk modeling, portfolio optimization, and operational risk modeling. Prior to joining Fidelity, Igor worked as a research professor of financial machine learning at NYU Tandon School of Engineering. Before that, Igor was an executive director of quantitative research at JPMorgan and a quantitative researcher at Bloomberg LP. Igor has published numerous articles in finance and physics journals and is a frequent speaker at financial conferences. He has co-authored the book Machine Learning in Finance from Theory to Practice and Credit Risk Frontiers. Igor has a Ph.D. in theoretical high-energy physics from Tel Aviv University and a Master in Science in nuclear physics from St. Petersburg State Technical University. Please join me in welcoming Igor Halperin.
Thank you very much, Nadia. Thank you for this kind introduction. Let me share my screen and jump immediately to my presentation, given that we don't have much time. And the previous time I was trying to present this, I ran out of time, so I apologize ahead if this happens again. But I was told by the organizers that there is some flexibility today because I'm the last speaker. So we hopefully, but I will not abuse this opportunity given to me. All right, so I announced my presentation as Introduction to SciPhy RL, and this is another version of this talk. So you see here these acronyms SciPhy RL and Dr. L, and Dr. L stands actually for Distributional Offline Continuous Time Reinforcement Learning. And I'm going to present an approach to this sort of reinforcement learning that connects to deep learning and actually solves the resulting differential equations, partial differential equations, using deep networks. All right, now the other thing I wanted to add is that this is a new work, which I have a paper which is available on arXiv on that. Even though the whole framework was designed to work with financial problems, this first paper and actually this presentation as well will be very general and will not talk about financial applications at all. But towards the end, we can briefly talk about that as well. So I just ran out of time and didn't have enough time to show you like examples specifically how it works in financial setting. All right, so here's the plan of my talk. First, we will talk about why continuous time reinforcement learning, for short CTRL, is interesting and useful. And then I will talk about how you can do distributional offline CTRL and why this is interesting. And then we'll talk about the HJB equation. HJB stands for Hamilton-Jacobi-Bellman equation. That's the most classical equation of optimal control. And in this work, I will present you a kind of a version of this, which I call soft HJB equation. And then we will talk about what SciPhy RL is and how it solves this soft HJB equation using neural nets and neural PDEs. And I'll talk a little bit about the thing that the final algorithm I call deep Dr. L solver. And I'll show you some examples and then the conclusion. So let's first start with the reinforcement learning itself. So just to remind to those of you who are familiar or not familiar with reinforcement learning, anyway, we start from square one and talk a little bit about the general setting of reinforcement learning. So in reinforcement learning, you basically solve a problem of some agent that who has to act optimally over some sequence of time steps. So the whole process extends over time, right? But at each time step, the process of interaction of this agent with the environment is basically the same. So at each time step, the agent receives some information about the state of the environment, which is codified in some sort of a state. It is a state vector. It might be a multi-component vector, which describes the state of the environment. I call it S here, right? So this is the information that goes from the environment to the agent. And then upon receiving this information, the agent acts. So the agent acts using some set of available actions to the agent, and this action is denoted as AT. So for trading, it would be like this thing would be the state of the agent's portfolio and also state of the market. This would be the information that goes from the market to the agent, so which would include both private information to the agent and market-wide information. And the actions of the agent would be the trades in the portfolio. Right, so there are these two things, and there is another thing called reward. So reward is actually what defines what the agent does, and the ultimate objective of the agent is to maximize the total reward from taking action. So rewards are in general a function of the state and action. So upon taking action A, given state S, the agent receives some reward, and the objective is to maximize the total reward over the course of action. Now, there are a few complexities here. First is that because the process extends over time, then choosing actions should involve some sort of planning into the future and forecasting as well. And second, there is another potential applications which may or may not come up in your particular applications, which is the presence of this feedback. So what is this feedback? This feedback codifies the possibility that by acting on the environment, the agent can also change the environment. So it's like a butterfly effect from Great Bradbury's story, if you're familiar with this story. And this feedback loop is pretty unique to reinforcement learning. But this whole formulation is actually nothing but the generalization of very classical methods of optimal control, which were developed in the 50s by Robert Bellman. So it's Bellman dynamic programming, which are designed to work with real-world problems. The classical approach, unfortunately, does not work for most problems of practical interest, which are more than like very low dimensional, more than maybe 2 dimensions, so 3 dimensions. All right, now this is a brief sketch of the math involved, or rather, I should say, the notations. So in most of approaches to reinforcement learning, we deal with the setting which is called the setting of Markov decision process, which is fully observable environment, where the dynamics can be modulated by agent's actions AT. So the blue dots here are states of the environment, denoted as S1, S2, etc. which belong to some set of states S, and it can be discrete or continuous. Likewise, the actions here, these green dots, are chosen from a set of possible actions, denoted as A, which can also be discrete or continuous. Transitions between different states here and here are conditioned on the actions, and they're called conditional transition probabilities. So this is the Markov setting in which probabilities of the next state are only defined by the previous state, but not the history, as shown here, and in addition are conditioned on the action. Now, upon taking all these actions, the agent receives reward, which is shown here, right? So it's a reward function is a function which maps this product space onto the real line. And finally, most of formulations of reinforcement learning introduce the so-called discount factor, which is the number between 0 and 1, and it shows like how much immediate rewards are preferred to more rewards which come from the future. And then finally, having defined all this, we define the cumulative reward function, which is given by this expression, the sum over all times, or a discounted sum, right, of the reward, right? So this is the thing that we want to optimize. However, we cannot optimize it directly because it depends, as you can see here, on the future values. And if you're here, then it depends on the future. Because of that, you can only maximize the expected value of this total reward. And related to this, people usually operate with two sorts of value functions. One is called the value function, which is just the expectation of total reward conditional on your current state, initial state, and time t. And another one is called the action value function, which is the same thing, the same expectation, however, conditioned on the initial state and initial action as well. Right now, the problem of reinforcement learning is now solved by choosing what is called the policy. So the policy is actually the rule which gives you a prescription of what the agent should do upon each different state of the world at each point in time. So it's a function which maps the states to actions. And this function can be either deterministic or it can be stochastic. So if it's stochastic, we're talking about stochastic action policies, right? And there is a mathematical equation, which I do not show here, which I'll show a version of it, that describes what the optimal value function, which is this thing optimized over all policies, should satisfy. It's called the Bellman optimality equation. All right, so this was the ultra brief introduction to reinforcement learning, the classical reinforcement learning, which is usually considered as a discrete in time process. Now we can ask the question, what would be the advantages of considering continuous time reinforcement learning? And there are many. One of them is that when you have multiple time steps, then approximation of a continuous time may be useful in practice. It can also connect problems with different time steps. So for example, if you have a discrete step formulation, and then you increase the time step by a factor of 2, how these two problems are related. If you start with the continuous time formulation, you can easily find the answer to this question. And another reason is that of mathematical convenience. So when you replace discrete time formulation, which produces difference equations, by a continuous time formulation, you end up with a partial differential equation, which is called the Hamilton-Jacobi-Bellman equation. And as long as it's a PDE, and there are tons of different numerical methods you can apply here. So this was about continuous time reinforcement learning. Now, what about distributional offline continuous time reinforcement learning, which you can call, which I call Dr. L for short. So why offline RL? offline RL comes in many different situations. So there are many more examples in real life or in finance and other applications in which we have previously collected historical data, which was collected by some other agent. It could be a human, it could be a machine, whatever. But it was data collected under some policy, which is normally referred as behavioral policy in this case. And the objective in this case would be to learn to act optimally just using this historical data, which is actually pretty much the formulation which is common to most of problems in finance. In finance, you have historical data, and you have to use this data to learn something. Right? Now, the difference of this setting from conventional reinforcement learning, I mean more standard one, is that in standard reinforcement learning, the agent here has access to this environment. Right? So the agent can try some new actions in order to optimize policy. However, in distributional reinforcement learning, there is no such luxury. So the agent should only learn from fixed data, right? So this formulation is very potentially widely applicable. So because we have so much of data that could be treated this way. However, it's also hard, exactly for the same reason, because the agent cannot explore different actions and can only rely on a fixed data set. It suffers from so-called exploration errors. So it can go pretty wrong unless you make some special efforts to tame it. All right, so this is about offline RL. Now, what about distributional RL? This is a very important point, I think, especially for finance. And it has to do with the following thing. When we're talking here about optimizing policy, right, so you can see that the value function is determined as the expectation of future reward, right? So you can the standard reinforcement learning algorithms, what they do is they maximize this expected value, right? But optimizing only on average may not be sufficient for many problems, right? Recall this old joke that if you stick your head to the fridge and legs to the oven, then on average you will be just fine, right? So it's something like that can happen here, right? So sometimes you care not about just average, but about some safety net, right? So you want to be good not just on average, but with some guarantees. And in this case, what people consider, they consider the so-called distributional RL. So basically, instead of this expectation, think of distributional RL essentially about learning the distribution of this total return, and not just its expectation. All right. Now, the other name for related approach is known as risk-sensitive reinforcement learning. Now, the previous methods, so both these methods, they go beyond optimizing just the expectation, but rather trying to control the whole distribution. And most of them are based on sample-based time difference methods. Now, what my approach does is another way to think about distributional RL, which is based on probabilistic approach and produces partial differential equations. The advantage of doing that is that these exploration errors, which are hard to control in more conventional offline RL approaches, can be now handled in a principled way. Because of reducing to some sort of regularization driven by partial differential equations. All right, now in the remaining few minutes, there is lots of math here, and I apologize in advance that I do not expect you to follow these methods just for high-level overview. All the technical details are given in the paper. But I just wanted to give you some sort of flavor of what is involved here. So there are a few elements here. So first of all, because we're talking about a continuous time formulation, the prime object of this formulation would be some sort of the integral. Now, I also changed the notation here a little bit. People who do control theory, they mostly talk about costs. So if you're talking about costs, then you have to minimize costs, but mathematically it's equivalent to maximizing rewards. So if you define rewards as negative cost, then minimizing cost would be equivalent to maximizing rewards, right? So there is one-to-one correspondence. But the other thing which makes it different from the discrete time reinforcement learning is this thing. In discrete time reinforcement learning, you had discrete sum over all times, right? While now this discrete sum is replaced by an integral over intermediate times, and this integral also involves some discounting. So this is the prime object, and this object can be called cumulative cost at time t. And now this cumulative cost is computed. T is the current running time, which is anywhere between the initial time, which is shown here as 0, and the terminal time, capital T. Right? Now, for arbitrary intermediate time t, this is obviously a random quantity because it depends on the future. But you can split this integral in two components, one running between integral from 0 to small t, and other from small t to capital T. Now, if you do it this way, then this thing is already known at time small t, and this is yet unknown, and therefore it's convenient to select this deterministic component, realized cost at time t, and call it CT, and write it in this way. And then also the one additional step that is done here is I extend the state space by extending this previous state space description as x by switching to extended vector which includes both x and this running cost, right? So now this is my extended state, and a extended state action space would be respectively would contain both y and action a, right? So now the dynamics are Markov in this extended state action space, and this is actually what allows me to derive an extension of the AGB equation, right? And the way it's done in this approach is the following. We need to do one more step here, which is related to this distributional thing. So if we work with the conventional risk-neutral reinforcement learning, then we would just take this running cost, this cumulative cost in time t, and would maximize this expectation value. So the expectation of this thing would be split as this, right? And we would proceed according to this line. But we want to do distributional RL instead. So we want to not just minimize the expectation, but we want to kind of control the whole distribution. And the way to control it would be by introducing some sort of the penalty of how much, how narrow you want the distribution of this total cost to be. And this can be controlled by this function. I call it negative utility. Why negative utility? Because this is something that you want to minimize rather than maximize. So, for example, you can take this square function, and this would define for you this objective function, which would be probability to get a particular value of the total cost, this small z equal, so it's the terminal value of the total cost, and you compute this conditional probability of having any particular value of this total cost by time, capital T, and then you take the integral of this equation with respect to this function, which basically penalizes how much you want to shrink it to zero. Right. So this is the prime objective. Now, in reinforcement learning, in this sort of reinforcement learning, we don't directly optimize this objective, but we rather take regularized version of this. So we add to this KL divergence between what and what. KL divergence between your yet unknown optimal policy, which is called pi here, and a behavioral policy, pi naught. And behavioral policy serves here as a kind of reference policy, or prior, if you wish. Now, these two things, the strengths of these two terms is controlled by regularization parameter 1 over beta. It's 1 over beta for historical reason, and beta is traditionally called the inverse temperature. So if you take this inverse temperature if you take beta to go to infinity, then this term will drop out, and then you'll end up with the classical deterministic policy and classical AGB equation. And in opposite limit, this term will be dominant. So when beta goes to zero, this term will be dominant. So optimization of this thing would essentially amount to optimization of this thing alone, right? And minimization of this thing, if you're familiar with scale divergence, its minimum is achieved when this guy is equal to this guy. So basically, it will enforce the proximity of your policy to your behavioral policy. All right. All right. So once you have this expression, then you define what is called the optimal cost function. So it will be just the minimum of this expression that I just showed with respect to all policies. And you should also supplement it by proper terminal condition, and you can check the terminal condition is just given by the value of this negative utility function at the value of terminal cost. So these two things can be reworked into a sort of a continuous time partial differential equation, which generalizes the deterministic HAB equation. Now it can be done for pretty general specification of your state dynamics. And for this, I've chosen this multidimensional diffusion process, which has so it describes the changes of the state vector as a diff part and a diffusion part, where WT is the n-dimensional Wiener process, and in this formulation, A is the random action. So this random action should be drawn from a policy pi, and the mathematical derivation, which I skip here, which you can check in the paper, shows that actually what enters the final PDE is not this original diffusion, but rather the original diffusion integrated with respect to the policy. So you replace this drift function and diffusion function by their integrated versions, which are defined here. All right, and by considering it's pretty standard steps how you derive this PDE. You basically take your value function and you consider infinitesimal change, how it changes when you shift time and its argument a little bit, and this is how you derive a PDE. So the soft version of AGB equation is derived in two steps. First, you derive what is called the backward Kolmogorov PDE, where the policy is fixed, and this equation is shown here. It's some sort of a PDE. Right? Now, with this PD, you can find the optimal policy analytically and then plug it back into this equation. And this actually gives you this extension of the AGB equation in a more general form, which is shown here. So what you can see here is it's some sort of a complex integral differential equation, because it involves partial derivatives of your value function with respect to your state and your cost, but also it involves this integral over actions with a weight given by your prior or behavioral policy. So it's not it's workable, but not the easiest thing to work. However, if you make your definition of the process a little bit more constrained, as shown here, so instead of most general specification of the drift and diffusion term, as shown here, I can take more specific expressions, as shown here, and more specific expression for the cost. Then in this case, things become more tractable. And also I take the prior policy to be a Gaussian mixture. So these are simplifications which I take in order to simplify a little bit the formulas. And in this case, it turns out that if you start with the prior Gaussian policy given by, prior policy given by Gaussian mixture, then optimization of this policy also leaves you in the class of Gaussian mixtures, which is shown here, where weights of these mixtures, means and the variances now all become functions of your yet unknown optimal value function, as shown here. So all this analytical expression give you this functional dependence, and with this specification, this optimality equation becomes a semi-linear equation. Actually, it's semi-linear. So you see those terms are linear in the derivatives, partial derivatives, but it's semi-linear because of this nonlinear dependence on the value function. So now it's a nice equation, and we can try to solve this equation directly from data, and this is where we connect to this offline RL. So usually when people have AGB equation or things like that, they solve it from the model to they first define the model dynamics, and then they do some sort of simulation or something like that, and then solve this equation. Now, in the setting of offline reinforcement learning, we should treat this equation differently. So we say that we have data which is somehow related to this equation, and then we use this data and basically solve this equation from data, right? Now, for this particular case, it's a little bit more tricky because the data that we see is not data directly related to this equation, because this equation defines it describes the optimal value function, right? Optimal value function assumes optimal policy, but we're not given the optimal policy, we're rather given the behavioral policy, right, which might be suboptimal. Nevertheless, for this particular case, the trick which can be done here is that you can relate, you can use exact likelihood ratio in order to visualize your behavioral policy, your results of behavioral policy. You can visualize as tweaked results from optimal policy. Essentially, and this is given all the details are in the paper, but schematically it looks like that. So you can express probability to see the data that you see as data sampled from the optimal policy, which I called here by this letter, and you can relate it to something what you see which is data sampled out the behavioral policy, which I called here pi sub 0, by some analytical function. And then if you have it, some analytical function which involves again your unknown yet value function. And if you do that, then you can combine these two things together in order to learn your equation directly from data. So you would use this exact likelihood function in this part, and the model mismatch you would codify. I didn't have time, unfortunately, to explain this part, but the idea here is that once you have the PDE itself, you can switch to sample-based view of this PDE and use pathwise formulation of these dynamics. And if you do that, then you would translate the original equation into like some sort of a pathwise equations, which would and then you would use it together with this likelihood estimation in one log likelihood function, which combines the penalty, two sorts of penalty. One, it combines the penalty for the model mismatch as implemented by the neural network, which is shown here. So we now parameterize our value function by a neural network with some parameters, which we call theta, right? We express our these terms in the equation in a path based formulation of the equations into some new object that I called Hamilton-Jacobi Hamiltonian. And this gives you this whole term, which is the model error. You combine it with the sample error, with the errors from the path, and then you get one log likelihood function. And then you just minimize the negative log likelihood of this function with respect to parameters that define your optimal value function through your neural net. So essentially what it achieves is that this gives you a formulation of offline RL as a version of straightforward supervised learning. And it solves the problem of optimization of the policy in one step, which is kind of the most attractive point about this whole thing. So by doing things this way, you get rid of like things such as value iteration or policy iteration, which typically are used for reinforcement learning and make it very slow. All right, so let me skip this discussion, and I'll just show you, like in the remaining 2 minutes or so, I'll show you numerical examples. So in the paper, I gave some illustrations of how it works by simulating data using a simple specification of the drift and costs and diffusion terms. So I simulated, I did two sorts of experiments, 10-dimensional state space and 5-dimensional action space. And another one was 100-dimensional state space and still the same number of dimensions for the action. And in both cases, I simulated 10,000 trajectories. The important point to note is that I show like subset of 100 trajectories here. All of them, you see like very limited range of the state, right? So for this particular case, the values of x were between this and that, which is important in terms of learning. Now, so I train it, right, and I get some learning curve. The training took about 8 minutes on pretty old Mac laptop. And then once I trained, I explore how well it works. So I basically take my trained value function. I can compute because I use PyTorch, I can have analytical derivatives. I can compute all the terms which define the optimal policy as a theoretical expression. And then I can apply it for arguments which were not seen, which is an important point, which were not seen in the training data. And this is what is shown here. So I show components of the means of my stochastic policy. So I had 5 dimensions. So I show 5 curves here. For 2 components, I used 2-component Gaussian mixture for illustration. So this component number 1, this component number 2. And what you see here is that I have very smooth, the behavior that I get is very smooth, and actually shows the ability to extrapolate, which is extremely important, right? So it can go beyond the data that I show it. And the same behavior is obtained for 100-dimensional case. The only difference is that it takes longer. It took, in my case, about 45 minutes to train, but the behavior is again the same. So again, I see very smooth curves which are able to extrapolate. And therefore, I believe that this solves this problem of extrapolation of offline reinforcement learning. Right. So here's my summary. SciPhy-RL, I forgot to mention that the name SciPhy-RL comes from combining 2 things, scientific ML and physics-based neural nets. Because I combined the elements from both, I decided to dub this whole approach SciPhy-RL. And Dr. L with SciPhy-RL amounts to solving the soft version of AGB equation directly from data. It does it in one step, unlike many other offline reinforcement learning methods. It does it in a matter of minutes rather than hours, even for pretty high-dimensional data. It can be extended in multiple ways, including like nonlinear dynamics, including online version, etc. And it can be applied in many for many different applications, even though the original development was done with financial applications in mind. So this is the original reference, and for some extras, I could recommend the final chapter of our book, which talks about multiple connections between machine learning and reinforcement learning in particular, and physics. And I would like to stop here and take questions. What's the best way to set up reinforcement learning environment? Can you describe your hands-on experience of an example of defining the reward? Reinforcement learning environment is actually set up like you decide how to set it up. There are many environments which are available from libraries, even though most of those libraries, such as OpenAI, GIM, they are not specifically tuned to financial applications. There are versions of this or some sort of add-ons which provide financial environment. So I saw something called Financial GIM, things like that. It really is specific to the problem that you're trying to solve, right? So I saw many examples of financial environment for, let's say, optimal execution or high-frequency trading. This is not what I do, but if this is what you do, you can use that. Hands-on experience of an example of defining the reward. This is absolutely the key point. Very important. So in what I did, most of my work, I tried to find formulations which actually allow you to proceed even without using neural nets. And this is doable indeed if your reward function is simple enough. So if your reward function is quadratic in states and actions, and then the statement is that you can proceed without neural net altogether. But whether it's feasible in your particular case or not, or advisable, it's a question which should be addressed separately. So if you're lucky enough and you can proceed with quadratic rewards, then you can save yourself lots of efforts, because everything that you do can be done like in a transparent way. What language did you use to build and test this? PyTorch. Is there an example in Python available in GitHub? I can't share, unfortunately, my code because it was done on the work computer, but there is a volunteer who's trying to develop a public version of this code and put it on GitHub. I don't know where she is on her work.
Thank you so much, Igor. It was a very interesting presentation, very detailed. Let's see if we can get another question. Let's wait just a minute, and if no question comes, we can close here the presentation.
Sure. I saw 2 questions so far, which I already answered. Yes.
You did such a great job. Thank you so much.
Thank you.
Okay, we do have a last question.
What are your opinions on quantum RL? My opinion is that I want to learn more about it. That's my opinion. That's my plan, actually. Quantum RL and quantum machine learning look very interesting. But you have to be very careful about what you want to do with that, right? So I'm not entirely sure that problems that people discuss for potential applications for quantum computing and quantum RL are the best applications in terms of maybe, like what I'm trying to say is that quantum computing is most useful for modeling things which are quantum in nature, right? But when you try to feed them to some classical problems, then you have this embedding problem, which can negatively contribute to performance and make the whole thing very complex.
Okay, so I think we can close it here. So
Yes.
I want to say thank you, Igor. Thank you so much from all TMLS for joining us today. And good luck with your book. Seems really an interesting one. So
Thank you very much. Thank you very much. And thank you for inviting me. I understand you guys have a thriving community in Toronto.
Yeah, it was really our pleasure.
People talk about it on LinkedIn that becomes a major hub.
Thank you so much.
All right.
Bye,
Thank
everyone.
you. Thank you. Take care.